Hello, dear viewers, a warm welcome to all. In this module, we are discussing three important types of carbon-based nanomaterials, namely carbon nanotubes, graphene and carbon dots. First of all, carbon nanotubes. Picture represents some types of carbon nanotubes. Let us enter into the details of carbon nanotubes. The prime focus of carbon nanotubes in this discussion includes introduction, discovery of carbon nanotubes, synthesis, purification, different physical and chemical properties of carbon nanotubes, and application of carbon nanotubes. Carbon nanotubes are cylindrical molecules that consist of rolled up sheets of single layer carbon atoms, that is graphene. In this picture, it is clear that the graphene sheet rolled up to get a single walled carbon nanotube. In a similar way, if more than one graphene sheet rolled in the same pattern, we will get multi-walled carbon nanotube. It can have more than one layers, that is multiple layers can be rolled. Like their building block graphene, carbon nanotubes are chemically bonded with sp2 bonds. Extremely short, extremely strong, high force of attraction is created from this sp2 hybridization. Classification of carbon nanotube is based on their structure. The two types are single-walled carbon nanotubes and multi-walled carbon nanotubes. In a single-walled carbon nanotube, there is only one layer of graphene which is rolled to a cylindrical form. However, in the case of multi-walled carbon nanotube, several layers are rolled to get the multi-walled arrangement. The multi-walled carbon nanotube is analogous to the arrangement of PVC pipes, such that one small pipe can placed inside a bigger one, like that. This represents the arrangement of multi-walled carbon nanotube. Here, the small diameter nanotube is placed inside those with the bigger diameter. However, in SWNT, there is only one layer rolled up. The single-walled carbon nanotubes can be further classified into different types. The classification is based on some vector parameters or simply a chiral vector CH. The chiral vector CH is equal to n vector d1 plus m vector d2, where n and m are two integers which refer to the number of d1 and d2 vectors. d1 and d2 vectors are unit vectors of a 2D graphene lattice based on the values of n and m. That is, the two integers n and m, we can classify SWNT, single-walled carbon nanotubes, into different types. The different types are zigzag nanotube. In the case of a zigzag nanotube, in m and n, the value of m is equal to 0, but n not equal to 0. However, for the next type, that is nothing but armchair carbon nanotube, both the values are same. That is, value of n equal to m gives armchair nanotube. Another possibility is chiral nanotube. In the case of a chiral nanotube, the integer n not equal to m, both not equal to 0. Thus, based on the value of N and M, we will get zigzag, armchair and chiral single-walled carbon nanotubes. Picture represents the armchair, zigzag and chiral single-walled carbon nanotubes. First of all, armchair nanotube, as I mentioned here, the integer N is equal to M. Second one, zigzag nanotube, here N not equal to 0, but the second integer M is equal to 0. Finally, the chiral single-walled carbon nanotube, for which N not equal to M and both not equal to 0. Another part of our discussion is a comparison between single-walled carbon nanotube and multi-walled carbon nanotube. Let us analyze the features of both. First of all, single-walled carbon nanotube. As we are aware, it is a single layer of graphene. Multi-walled carbon nanotube, it is multiple layer of graphene rolled to form the MWCNT. Bulk synthesis of single-walled tube is difficult. However, bulk synthesis of multi-walled carbon nanotube is comparatively easy. SWCNT not fully dispersed and form bundle structures. However, MWCNT form homogeneous solution. In the case of single-walled carbon nanotube, the purity is not up to the mark. However, in the case of multi-walled carbon nanotube, purity is high. A chance of defect formation is there in SWCNT during its functionalization. However, in the case of multi-walled carbon nanotube, there is minimum chance for defect formation. Finally, single-walled carbon nanotube can be easily twisted and more pliable. However, multi-walled carbon nanotube cannot be easily twisted. That all about the comparison between SWCNT and MWCNT. Regarding the discovery of carbon nanotubes, the first CNTs were reported in 1991 by Sumio Iijima at NEC laboratory Tsukuba in Japan. He discovered multi-walled carbon nanotubes in carbon soot made by an arc discharge method. This discovery is one of the landmarks in the field of nanotechnology. Later on, in an interview, Iijima revealed that the discovery was unexpected, quite unexpected, but not entirely accidental. That about the discovery of carbon nanotubes. Another aspect is synthesis of carbon nanotubes. In the previous modules, we are familiar with different type of synthetic strategies for nanomaterial synthesis. And for the synthesis of carbon nanotubes, we mainly adopt three methods, namely arc discharge method, laser ablation of graphite and the well established chemical vapor deposition. In the first two processes, graphite is combusted electrically or by means of a laser, and then carbon nanotubes developing in the gaseous phase are separated by suitable methods. All three methods require the use of metal catalysts. The catalysts commonly used are iron, cobalt or nickel. In the last procedure, that is the chemical vapor deposition method, which is highly promising. This is because it allows the production of large quantities of carbon nanotubes under easily controllable conditions. Comparatively, CVD procedure is a low cost procedure. It is also suitable. The CVD process can be purely catalytic or supported by plasma. The latter requires slightly lower temperature than the former. That means catalytic conditions requires high temperature, but plasma process is supported by low temperature. Now, purification of carbon nanotubes. Carbon nanotubes prepared by different methods may have several impurities. These impurities include carbonaceous impurities or metal catalyst particles. Therefore, purification is essential prior to applications of carbon nanotubes. What are the common methods for the purification of CNTs? The common methods are gas phase oxidation, electrochemical oxidation, centrifugation, ultrasonication, and microwave purification. Regarding the properties of carbon nanotubes, it is more fruitful to have a comparison in properties of different carbon allotropes. From the chart, it is clear that the different allotropes, coal, graphite, diamond, buckyballs, and carbon nanotubes have different levels of hardness, tensile strength, thermal conductivity, and electrical conductivity. From the chart, it is clear that carbon nanotubes have excellent hardness, high tensile strength, better electrical conductivity, and better thermal conductivity compared to all other allotropes. Electrical conductivity of carbon nanotubes is 6 times greater than copper. As we are aware, copper is a better electrical conductor. Its conductivity, the conductivity of metallic copper, is less than carbon nanotube. That is, carbon nanotube is a very good electrical conductor compared to metals. The carbon nanotubes can be metallic or semiconducting depending on the chiral nature of its structure. They have tunable band gap. Carbon nanotubes can be tailored for different electronic properties. They have very high current carrying capacity. They can perform as excellent field emitter. These are some important properties of carbon nanotubes. Regarding mechanical properties of carbon nanotubes, some points should be kept in mind. Carbon-carbon bonds are one of the strongest bonds in nature, as we are aware. Carbon nanotubes composed of perfect arrangement of carbon-carbon bonds, and carbon nanotubes are associated with extremely high Young's modulus. Let us compare Young's modulus of some materials like steel and diamond with SWCNT. Steel is having Young's modulus 190 to 210 gigapascal. For diamond, it is between 1050 to 1200 gigapascal. But for single-walled carbon nanotube, it is 1000 plus gigapascal. Some unique properties of carbon nanotubes. Carbon nanotubes 200 times stronger than steel of the same diameter. Carbon nanotube is the first synthetic material to have greater strength than the spider silk. Excellent conductors of electricity and heat, have huge potential applicability for the product development. Regarding the applications, we have to discuss electrical, energy storage, biological applications. Electrical applications include field emission in vacuum electronics, usage as the building block for next generation VLSI systems, used in nanolithography, and about the energy storage applications of CNT. They can be used in the development of lithium batteries, for hydrogen storage, and in the subtitle of biological applications. Carbon nanotubes can be used as biosensors for developing functional atomic force microscopy tips, then for DNA sequencing. Biological applications are more relevant than other applications. Biosensing is one important application of carbon nanotubes. In biosensing, many spherical nanoparticles have been fabricated for biological applications. However, nanotubes offer some advantages relative to common nanoparticles in the following aspects. Larger inner volume of carbon nanotube enable the filling of it with the chemical or biological species. Open mouth of nanotubes make inner surface accessible for further functionalization and for further changes or reaction. Distinct inner and outer surface can be easily modified separately. Thus, CNTs are highly favorable for biosensing applications. AFM tips can be constructed based on CNTs. This is favored by small diameter, which implies maximum resolution, excellent chemical and mechanical robustness of the carbon nanotubes, and high aspect ratio of the carbon nanotubes. DNA sequencing is another important biological application where we utilize carbon nanotubes. Nanotubes fit into the major groove of the DNA strand. Applying bias voltage across CNT, different DNA base pair gives different electric signals. Hence, DNA sequencing is made possible. With multiple carbon nanotubes, it is possible to do parallel, fast DNA sequencing. Graphene and its derivatives are another important type of carbon-based nanomaterial that we considered in this discussion. What is graphene? It is an allotrope of carbon consisting of single layer of carbon atoms arranged in hexagonal lattice. It is a basic structural element of many other allotropes of carbon. It can be considered as indefinitely large aromatic molecule, polycyclic aromatic hydrocarbons. Graphene is the name for an atom-thick honeycomb sheet of carbon atoms. Graphene is harder than diamond, more elastic than rubber, tougher than steel, yet lighter than aluminum. Its high electron mobility is 100 times faster than silicon. It conducts heat 2 times better than diamond. Its electrical conductivity is 13 times better than copper. Discovery of graphene. Graphene was first demonstrated by two scientists, Andrei Jim and Konstantin Novoselov. They were physicists from University of Manchester. They extracted graphene from a piece of graphite such as is found in ordinary pencil. These two scientists won Nobel Prize in Physics in the year 2010. How graphene is made? The quality of graphene plays crucial role in different aspects. The following factors have adverse effect on its electronic as well as optical properties. What are such adverse facts? They are defects, presence of impurities, grain boundaries, structural disorders that may occur in it, wrinkles in the graphene sheet. All these are adverse factors on electrical and optical properties. There are several methods employed for the synthesis of graphene. Each method has its own advantages and disadvantages. The most common techniques for the synthesis of graphene are micromechanical cleavage, chemical vapor deposition, epitaxial growth on silicon carbide substrate, chemical reduction of exfoliated graphene oxide, liquid phase exfoliation LPE of graphite, and finally unzipping of carbon nanotubes. Regarding the electronic properties, graphene is one of the best electrical conductor. The unique arrangement of carbon atoms in graphene allows electrons to travel easily with the high velocity. Graphene remains capable of conducting electricity even at the limit of nominally zero carrier concentration because of electrons doesn't seem to slow down or localize in them. The electrons moving around carbon atoms interact with the periodic potential of graphene's honeycomb lattice, which gives rise to new quasi-particles. Regarding the mechanical properties, the graphene is associated with impressive mechanical properties such as stiffness, strength, and toughness. Stiffness is one important characteristic feature. The second order elastic stiffness in graphene is nearly equal to 340 Newton per meter. This value corresponds to an Young's modulus of 1 terapascal. Regarding the strength, defect-free monolayer graphene is considered to be the strongest material with a strength of 14 Newton per meter, which is equal to intrinsic strength of 130 gigapascal. The toughness, fracture toughness is one of the most important mechanical property of graphene. Another part of graphene is a derivative simply known as graphene oxide. Graphene oxide or GO is a chemically modified graphene containing oxygen functional groups such as epoxides, alcohols, and carboxylic acids. Chemical analysis reveals that carbon to oxygen ratio in graphene oxide is approximately 3:1. Picture illustrates the graphene oxide. Graphene oxide, by analogy to graphene, is single layer form of graphite. GO has been applied in several biotechnologies such as biosensors, cellular imaging, nanoprobes, as well as drug delivery. Very recently, graphene oxide based nanocarriers have gained significant attention for anti-cancer drug delivery. This is because of their high drug loading and effective delivery capacity. Applications of graphene, they can be used under several application titles such as energy storage and in solar cells, sensor applications, electronic applications, photo detectors, coatings, radiation shielding, lubrication purpose, and for water purification. The last type of carbon based nanomaterial that we considered in the present module is carbon quantum dot or CQDs. Carbon quantum dots are a new class of carbon material. Simply we can designate it as C dots. They are said to be the clusters of carbon atom with a small diameter. That is, the diameter is in the range of 2 to 8 nanometer. They are simply small carbon nanoparticles. CQDs were first discovered by Su and his co-workers in 2004. It is an accidental discovery during the purification of single-walled carbon nanotube. Carbon quantum dots are new class of carbon-based nanomaterial with different attractive properties. They are associated with high stability, good conductivity, low toxicity, environmental friendliness, simple synthetic route for its preparation, either top-down or bottom-up procedures, comparable optical properties to quantum dots. They are extensively investigated due to their strong and tunable fluorescence emission properties. They have prominent fluorescence which can be tuned. Finally, we are considering the applications of quantum dots. Superior properties such as low toxicity, which is highly favorable for biological and biomedical applications. Low toxicity and good biocompatibility render carbon quantum dots or C dots favorable in different applications such as biomedicine, optronics, catalysis, and sensoric applications. Note that carbon quantum dots are soluble, they can be modified, they are stable and highly biocompatible. Thus, in the present module, we discussed 3 types of carbon based nanomaterials, their preparation, properties and applications. That all about this module. Thank you.